last speaker, Sherub from UTS. Kiyoung Shuk, I understand is not here today, but is the other partner to this project from Ciotech. So I'd just like to hand over to Sherub just right now and just bring your presentation.
Thank you, Jason. Good morning, guys. Still. So I'm just trying to address some of the issues that we discussed in the morning about the sodium problem. I think this may be one of the solutions. I wouldn't say that this is the best solution. So I just want to acknowledge first the other contributors, Prof Sherub Phuntsho. How you is on master students who worked on this one. Dr. Pemadurji is not with us, but yeah, he's collaborated with us. Jade, and also Kyung Suk Kang from Ciotech, who is our industry partner, Associate Professor Leonard Tejing, and Sean, of course. So this is my outline. I'll just skip this one. As with the, if you look at the urine composition, so at around 2.5% is the urea, and also other inorganic salts around 2%, roughly. So of course the concentration varies, and also a little bit of organics is there. But what we are interested is the sodium that is between 1,000 to 4,500 milligram per liter, and the sodium itself. We try to relate to the calcium and magnesium, as I will see later on. So that's why the calcium between 100 and 300 milligram per liter, and magnesium 25 to 120 milligram per liter. So the issue with sodium and chloride is the toxicity, so ion toxicity. If you have a lot of sodium, then there are three things that impacts the ion toxicity, then osmotic stress that it induces to the plants, and also it, of course, that results in the reduction in the yield. The other problem is the soil degradation. So it displaces magnesium and calcium in the soil, and what happens is that it degrades the soil quality, and it results in aggregation of soil, reduced soil permeability, and poor aeration. So these are some of the problems that you can see from this picture, that if the sodium bond you can see in the leaves. So this is because of the excess of sodium in the soil. So this one way of measuring the water quality, for example, is when you irrigate, they use this called sodium absorption ratio, which is a relative concentration of sodium, as you can see from the equation there. And so if the relative concentration of the sodium with respect to calcium and magnesium is higher side, and in relative to the the total the conductivity, electrical conductivity of the irrigation water, if you're talking about, then there's a certain threshold that if it is within that line, for example, so if it's within that, if it is below this one, it's okay, that it doesn't really impact the soil. But if it is within that, it has a moderate, and anything above that, it is quite significantly damage the soil. So in our case, for example, we saw that just roughly the sodium absorption ratio is between 20 and 56 for the fresh urine, and if you dilute further, it goes to something like if you say, for example, usually urine could be diluted up to 5 to 10 times before you apply, and then if you do that, then the sodium absorption ratio reduces to around 10 to 18. But still in the long term, probably it's a problem. Earlier, Ami was saying that it may not be a problem in certain parts, like in the United States where there's a lot of rain, it can flush, but in Australia where the water is a problem issue, so you may not have that luxury of the rain flushing your the sodium deposits in the soil, so you may still have a challenge. So the other issue that we're looking at is that not only to the plants, but also it may also have some issue with the quality of the urine fertilizer itself, and then people may say, oh, that your sodium concentration is high, if people who are aware of the sodium problem. And also that when we are concentrating the fertilizer, the urine derived fertilizer, it again magnifies the sodium concentration. That becomes even more alarming. So that's why we try to see how we can remove the sodium. So removing sodium is is a challenge, because it's because there are many other ions present together. So we are looking at how we can use membrane capacitive deionization. That is electrochemical process. It's electrochemical process where we use anode and cathode, and there's an ion exchange membrane that allows only certain ions to pass through. And then we are trying to see if we can do this, apply this one. So the objective here is to evaluate the capacitive deionization, so membrane capacity, mCDI, to separate the urea and the ions. Ions can be separated based on this technology. So if we separate ions, at least we have sodium on one side, and then we can further process them and return it back. So this is the concept that we developed here. For example, if you have a urine here, and then but it has to be fresh urine, so you can't use with the hydrolyzed urine, because you have the urea is already converted. So here we use mCDI to separate urea and urine. Once the urea and the ions goes to the nanofiltration, and because ions, there are a lot of, besides sodium, we have calcium, magnesium, potassium, which is useful for that. We want to return using nanofiltration, return it back, and then join together. So urea that can go to the MBR process that we're talking about, and then the process it to convert it into nitrification. So now you have nitrified urine coming up, and then of course we can concentrate later using MDO. So that's what we have here. Sodium will be gone through the here. So probably something like we're expecting more than 50% of sodium could bleed out from the system. But we also lose some the other essential ions like potassium. So that's one of the challenges. So this is the CDI stake that we use in the lab. So this is the process. I don't want to describe. Maybe many of you know this. How we have a cathode and anode, and then cathode is positive, anode is positively charged, and then so the ions get attracted on each other, and so they are removing that way, separate. So these are some of the operating parameters that we used. Of course, we did with the synthetic urine. So the results I just want to present here. So just initially did the validation experiment. We have urea and just the sodium and chloride, no other ions. And you can see that, of course, this is a batch process, so we have to do it again and again and again. So you'll see that the concentration of the ions is going down, whereas the urea is remaining almost constant. So that means actually this is just proving that you can separate the urea and the ions, sodium and chloride ions. So other thing is that now we wanted to see how the voltage, because you usually apply at a constant voltage and then varying current. Usually we try to operate at a lower voltage, less than 1 volt, because you don't want to have this electrolysis happening. But as we try to look at different high voltage, and we try to operate at, my student operated at 2 volt, we see that one of the interesting things we observed was the pH was suddenly dropping at a certain point. pH was dropping, so we think that this could be one way of a good thing for us, because as Abram was saying, that we store urine under high pH, you put acid and all. So probably you don't have to put acid here, because you can generate acid through this water hydrolysis. Or here, if you could say, there's some water oxidation going on the anode side, so that this produces H plus ion, so that increases the pH, decreases the pH of the urine. So in that way, you have urea separated and a high pH, so probably can store the urine for urea for longer time, and probably it will have somehow Bezat's problem of storing and transporting the urea. So we tried out different influence of flow rates, and I didn't see many impact on that. There was not so much influence on the influence of flow rate. We did also absorption time. Yeah, absorption time, of course, it's the more the absorption time, the longer period it has to absorb the iron. So of course, if you have less time, if you have less absorption time, it takes longer time, and then you more cycles to do it. So it's this is what. But basically, look at the urea concentration, but it remains constant. That's one of the advantages we have, because it's not really absorbing on the CDI electrodes. So we also tried this one with the influence of salinity that we have. So of course this is not really impacting that. Of course we have to have a higher number of cycles batch process to concentrate all the urine ions. But urea is almost like similar constant. So this also, we also tried with different urea concentration, and also the impacts are almost the same. So there's not much impact, so I just want to skip. So the summary is that, the membrane capacitive deionization can be effective process for reducing the salinity in the urine. Of course, we will have to, combine with nanofiltration to bleed out, because if either you only have a urea solution that can be used, but the plants require other elements also, so you don't want to be thrown away. So nanofiltration is one. Of course, I'm not presenting the nanofiltration by Excel. We will be doing that one as part of the future study. And also we want to see, because it's additional cost coming in here when you put nanofiltration, we want to see how does the economics say about that. Okay, that's it all. Thank you very much. I think I just want to acknowledge our industry partner, Siontech and ARC, for supporting this. Thank you.
So we have about 25 minutes for questions before we let everyone go for lunch and a bit of a break. And there's obviously more question time then. So if I could ask all the presenters maybe to come up front. You can bring a chair if you like. It is 25 minutes. And then just let everyone get up the front first. And we have a mic, yes. Okay. So are there questions? Are there any questions? Or yes, Abraham.
Thank you. I have a question about that last presentation. It was very interesting. Thank you. I was trying to understand the level of salt that you said was of concern. Is it possible to go back to that slide? Was I reading it correctly that the conductivities?
This one.
That one there. Yes. Okay. The conductivity of 1.5 to 20 millisiemens per centimeter. That was the diluted urine. And,
yes,
okay.
that's the program.
And that chart there is for irrigation water. So if we look at 1.5 or 2, then that could cause damage. But my question was, isn't there a lot more irrigation water, a lot more liters of irrigation water being put down per acre than liters of urine? And what would the consequence of that be? Maybe doing, urine is a small amount of fertilizer, but then a lot of irrigation water. Would that overwhelm the effect of the urine?
I didn't look at that from that angle. I think you're right. If you're doing a mix of irrigation, but we're talking about here only if you're doing a field that only irrigates using the urine fertilizer, and I mean what we're trying to say is like you mix the urine and then irrigate right together with the irrigation water. But yeah, like I said, there's already sodium in the irrigation water itself, so that may also contribute. But yeah, we didn't really look at the detail of that one, but we're just looking at see how, especially when we concentrate the urine, it is really the sodium numbers really showing up, and it may be a little bit of fear for the people who are using, especially the farmers who are a bit reluctant to be using the high sodium concentration. Of course, if you dilute it, it goes down to the extent of how much you are diluting, but still we feel that it may have some negative impact on, not so much on the plant, but for the people who are buying the product for the use. So they don't want to be, say for example, if the farmers, they want to sell this, grow this food product using this, the urine and then a lot of sodium or something like that. And then maybe this is just from the perspective, the user's perspective. But yeah, scientifically I haven't really proved this. This is, yeah.
Thank you.
So you're saying it's possibly just for social acceptance perspective. It would be really good to actually quantify what's the impact of that additional sodium on top of the baseline irrigation water. I think that's.
But if you concentrate the urine fertilizer and then you're adding sodium, the irrigation water, it also contains sodium. It's again you're adding more mass on this, right? So that could be an additional problem, isn't it? If the sodium is already present in the irrigation water, yeah, because the mass is increased here, right?
Yeah,
so
just whether is that 20% or 100% or 1%. I think that's what Abraham was asking. I think that's it. Really needs to be done.
Yes, I think so.
So can I ask a related question? I'm just wondering if any of the work that Bernadette's doing up in Toowoomba is going to look at that in the soils and whether there's any accumulation over time with that as well?